The next topic we're going to discuss is commutators and commutator relations. Oops. So we're all used to the commutative property just working. We've seen it all our lives. You learned it probably like what, middle school? And then you get here and I tell you that doesn't work anymore. Let's see examples where that doesn't work and figure out the physical consequences of it not working for quantum systems. Werner Heisenberg was someone who spent a lot of time looking at commutator relationships, and he had to learn a bunch of new mathematics and develop some mathematics because they didn't know how to deal with this at the time. But a commutator relation, if we have operator A and operator B, that should be equal to A hat B hat minus B hat A hat. And the result of that is the commutator. If A hat and B hat commutes, then what do you think the value of that should be? Yeah. Because the order won't matter. Most functions you've probably considered do that. Those who took linear algebra or Calc 3, did you ever talk about that or no? Okay, fine. If A and B don't commute, oops, that should be a then. Then the commutator is not equal to 0. This is like when Lily said the other day, this is just weird and different. It's what all this class is. Let's look at an example of some operators, and let's figure out if they commute or don't commute. And how do we test that? So as an example, what is the commutator of, we have two operators, A is equal to x squared, B hat is equal to y. We're going to ask, do they commute? Okay, to figure this out, we need a test function, a test wave function. This is just some like dummy function that's it. And if A hat, B hat, psi, if that's equal to 0, what can we say? Yep. If they don't, what do we have to say? Yeah. We'll talk about what that physically means in a bit. But what that means is there's an inherent uncertainty in something if you try to measure two things at once. Mathematically, it's just bound that way, which seems incredibly weird because we can measure multiple things. Like, we can measure how fast I'm going and where I am for macroscopic size systems. But quantum systems, you can't. You can only know some things so well, and you're just limited at that. I don't know about you, but that's incredibly frustrating to me because I like to know everything, type A personality. I'm the person who has to plan everything in their day, and if like someone's like, let's be spontaneous and go somewhere, my entire day is ruined. Okay. Let's check this out then. Let's plug this in and see what we get. A hat is x squared. Oh, but let's actually first. Let's just plug in for A hat and B hat. Which one was A hat again? Squared. Yep, and B hat was y. And then we get y, x. I would organize these a bit differently. I like it to go x, y, and z. Does anyone want to organize it differently? How do you want to organize it? Oh, wait, no, I like x. Yeah, me too. I was going to say, if you want it different, get out of the classroom. No. Okay, let's reorganize this. This one doesn't change, right? What about that guy? Okay, and what are we going to get when we combine all those things together? Yeah. Did that kind of feel silly? Yeah, it's like, what would... That's dumb. Let's look at something where that isn't the case. What is the commutator of the position operator, x, and the momentum operator, px? X hat is one of the most simple operators you can find. It's literally just x. Px hat we've determined a couple times. What is it? Negative. Yeah. Okay. So we want to get this commutator, right? We need to throw in a dummy function. So we need to show this. And what's the other portion going to look like? And then our dummy function out, right? Let's look at just this one for now. Okay, x operator, what is that? Yep. And then the momentum operator. Yep. Which way do operators operate? To the right. So which one do we have to conduct first? yeah, we got to do that part first. Then we apply the next one second. Nellen, you're exactly right. What did you say about that derivative? Yeah, we have to apply it to our trial function. We don't know exactly what our trial function is, so we're just going to be lazy. And we would say it's equal to the derivative with respect to x. We don't have to plug in a function. That's for the math nerds. We don't have to worry about that. Okay, let's solve it all the way through then. What are we going to get in the end? Yeah. Okay. Let's do the second part. What's that going to look like? What was the momentum operator again? Yep. Yep. Oops. Okay. Operators always act in what direction? Yep. So in this case, which one do we have to apply first? That one's not going to happen first. Well, how did it look like for up here? Yeah. That one's the first one that gets applied. And what's the second one? Yeah. Okay, it seems kind of simple because we've already applied it here, right? Like there's nothing more to do. Okay. We get negative I h bar because that's a scalar. We got to take the derivative of this. Ooh. What rule do we have to use? Product rule. Yep. Okay, product rule says what? Yep. Mm-hmm. What? Is it minus? Yep. Okay. This is kind of nice because what's the value of this equal to? Yep. So you get negative I h bar psi plus x, that. Okay, let's plug everything into this expression that we have up top that we had for the commutator relation. Plug all that in. The first one we got negative I h bar this minus h bar psi. And I'm just applying the negative through here. Did I jack something up? I think the first part is missing an X too. It is. That's better. Whew. Okay. Let's apply the negative sign through. Jeez. Plus I h bar psi. Okay. How's this thing going to simplify? Yep, those cancel out. And what are we left over with? Yep. Did those operators commute? No, they do not. So therefore, if we look at x hat, mpx hat, what is their commutator? Yep, it's IH bar. The function doesn't really matter for what you plug in, because as you see, that derivative cancels out and you don't have to worry about it. So, do they commute? This is known as the Heisenberg uncertainty relationship. And we'll show how that connects to the Heisenberg uncertainty principle later on. Okay. So what does this actually mean? If I want to know the position of my particle traveling in the x direction, and I want to know its momentum, how fast it's traveling, what does that mean? Can I know them at the same time? No, I can't. There's this error or this uncertainty associated with them. That's really weird. That's the best we can do. We can know it that well. If we try to understand one of these more, the uncertainty increases in this guy. Okay. Now let's get even a little weirder. This is the last thing we'll do for the day. Am I okay to erase this? So that was for x and y. Or excuse me, x position and momentum. But what happens if we consider the position not in the x coordinate, but the y coordinate? We want to look at how fast it's traveling in the x. That we can know completely. So there is an uncertainty relation. For observables that do not commute. And this is sometimes called incompatible observables. We're going to make a little table. Oops. Oops, I'm sorry. We want to make this variable too, that one. So incompatible observables. We can't know x and px exactly. So we'd fill a block in. Could we know x and y at the same time? Yeah, shouldn't be a problem there. We can even know x in the momentum and y. However, if we try to look at y in the momentum and y at the same time, we can't do that. Same thing is true for the z direction. Oops, I colored that wrong. And you can show that. I don't know if it's this daily problem, but one of your daily problems, we'd look at x and y, and then like z and momentum and y, and did they commute or not? Okay. Are there any questions about that? All right.